So this is probably the uh, last lecture that I'm giving, and then we have already split. I kind of decided to do this lecture because most of you have opted for RTL front-end design, and secondly, even to learn UVM, we need to learn a system Verilog. And then we have left two topics which I think are important. One is a carry save adder, and the other one is a microprogram state machine. So I thought to cover these up so that, and then there will be a good time for us to split into groups for rest of the 4 lectures. So last time we studied about time shared architecture, pipelining, retiming, and today first we will study about carry save adders. And it's very important, and especially once we are mapping algorithms to silicon. Important aspect. Microprogram state machine is also an important aspect. Then, okay, चलें.
जी सर, another RE, thank you.
अच्छा, इससे पहले I want to give you another assignment, and I think this is assignment number 5. Okay, and it is about pipelining. And what I want you to do is part of the assignment is simple. I want you to design a pipeline based finding maximum of 16 numbers, like input 16 numbers, and register all of these values in 16 register like we did in our class as well. You just need to generate this, and then you have a large combinational cloud, and then this cloud is going to compute one maximum value and latch it in a register as well, and then output this from the module. So this is the first part. So the first part is that design a module which has 16 32-bit inputs. So it is going to have 16 inputs, and then a combinational cloud. A combinational cloud computes the maximum of the 16 values and latch the maximum in another register and also output it. And now I want you to put one stage of pipelining here, and because you are doing a design, so going back to the Verilog code and inserting a pipeline register would be very difficult. So what I really stress is that you make a pipeline based design first. So first you make a design that has a pipeline in it, and once you do that, perhaps the best way is to instantiate this finding maximum of 4 numbers 4 times, and then out of those 4 finding a number 5th time. So this may be a better way, that you have these 16 numbers getting in, and you make cluster of 4. So these are the 4, and you have a module where you are registering all these 4 and then also registering the output. So this will act as a pipeline register, the register that you are using to store store the maximum of the 4 inputs. So again you have 4. Again you do the exactly the same module which register all these 4s, and then find the maximum and store it in another register, which is the maximum register. So this register will act as a pipeline register. So then you have another 4, another 4. So with these 4s, you have another module, and because you must not register them, so the 5th time perhaps you have to rewrite this module, that it finds out directly the 4 values and then find the maximum. So maximum will be the maximum of the 16 numbers. So this perhaps is a better kind of an approach, that splitting it into 4, 4, 4, 4. But then I want you to solve a more challenging problem, and this is optional because I don't know how many of you could actually able to solve it. It is sorting, let's say, 8 16-bit values, and as we know, the sorting is more complex, and then adding one stage of pipelining, then 2 stages of pipelining, then 3 stages of pipelining, So that is a bit more complex problem to solve, adding multiple levels of pipelining. So first you need to draw that what your sorter is doing, as we did that in our initial classes. That sorter, you have 8 numbers, and what a bubble sorter would do is it takes 2, sort them out, then it has the third one, sort the results. So sorting means that you are swapping the value. Okay, so this is your comparator. Comparator would have a maximum value, it goes up, and the minimum value will stay here. And then it has another comparator. So it is again going to sort, means that it is going to rearrange, where the maximum value will go here and the minimum will go here. And then you have the fourth one, and again you do the sorting. Okay, and you keep doing this. So once you're pipelining, you need to find out where you have to pipeline, but you have to put a cut set, which will cut the entire design, because then you are going to hold rest of the values as well. So all those which are not being processed are to be put in the pipeline register, and that is what is important. Otherwise it will not be a synchronized design. So synchronization means that every cycle you can have new values, and all these pipeline register would ensure that you will have a throughput of a single cycle. It latency, maybe if you have only one stage of pipelining, you will get a result after 1 clock cycle. If you have 2 stages of pipelining, after 2 clock cycle, then 3 clock cycle, then 4 clock cycle. That is how you are going to get your results. So the assignment is an important assignment. I would urge most of you to do this question, the optional question. That is a real test of how good you can pipeline. Okay, so that is a real test, because that sorting is a computationally very intensive algorithm. Uh, so now comes the carry save adder. So many a times, once you are adding more than 2 numbers, if you are adding 2 numbers, you have to use a carry propagate adder. We call it a carry propagate adder because you have 2 numbers and you got to get an answer which should be just 1 number. Okay, but if you are adding 3 numbers, it is better not to get an answer which is how can you add 3 numbers? The 3 numbers is that first you have to add 2 numbers. So put a carry propagate adder which is adding 2 numbers. So you have this adder which is adding 2 numbers, get a result. So adders are very expensive from area and delay perspective. Okay, so then you add these 2 numbers. So this is called an adder tree. So usually if you are adding more than 2 numbers, you have to put an adder tree. So now you add these 2 numbers and you get an answer. Okay, this is called an adder tree. If you are adding 4 numbers, again you have to have this 4th number and put another adder. And adders, as if they are ripple carry adder, they take a lot of time. If you are adding 64-bit numbers, so you have like 64 full adder delays here, 64 full adder delays here, 64 full adder delays here. On the other hand, if you are using any carry any other adder where you compromise area over speed, like carry select adder, conditional sum adder, like we saw earlier, then it'll take a lot more area. So the best and very simple strategy is that you are adding more than 4 numbers, let's say 3 numbers. You save the carry, you don't propagate the carry. Okay, carry propagation means that you keep sending the carry to the next full adder, to the next full adder, and it keeps adding. Don't do anything. Just, for example, you add 1 plus 1 plus 1, answer is 1, carry is 1. So which goes to the next level of next bit level. Okay, so just put 1 here and put 1 here. So you are not propagating, you are saving. Save it for the next logic which will add these 2, and just using one carry propagate adder. So similarly, 1 plus 0 is 1, 0 carry, and 0 plus 1 is 1 0 0 and 1 carry. 1 0 1 is 0 1, so 0 and 1 carry. 0 1 1 is 0 and 1 carry. 0 0 1 is 1 and 0 carry. Okay, just with 1 full adder delay, you can collapse or compress 3 layers into 2 layers. That's what we call this a compressor. A compressor is a full adder layer, and we call this a 3-to-2 compressor. It will take 3 numbers and reduce them into 2 numbers with a 1 full adder delay. So this is very desirable, And because in most of the algorithms you are adding many numbers, so once you are adding many numbers, you first collapse all of them together into just two numbers, and then only you must add them using a carry propagate adder. So these can then be added using a carry propagate adder. Same is the case if you think about a multiplier. A multiplier does nothing but has to add all the partial products together. So once you are generating partial product of two numbers, let's say you are multiplying b with 4-bit a, so you take 0th bit of a and AND it with all the bits to generate one layer of partial products. Okay, so here is uh, the partial products. As we know that whenever we are multiplying so two numbers, and if you write them in binary, let's say this is one number, this is the other number, so you take this first, so this is the bit you take and multiply all this with 1. 1 means that you are going to have this first partial product is the same, which is your multiplicand 1 1 0 1. Then you take this one and shift them by 1 here, so it is 1 0 1 and 1. Now you take 0, so multiplied by 0 is all zeros, so 0 0 and 0 and 0, and then you take 1 again, and then you have to add all of them together. So this becomes the same case. Once you are adding more than two numbers, never add them using a adder tree. Just compress them till the point you have only two numbers left, and then add these two numbers using a carry propagate adder. So we are going to do the same, that this is how you generate partial products, and instead of just putting so many adders to add them together, you use compressor. And how you use compressor? By going, you say, okay, this is 1, no compressor is required, this is 2, you can use a compressor which will 2 bits add and carry. And now these are the 3 bits, so you use 3 bits and you have a sum and a carry to the next location. Then you take this next 3, you have a sum and carry in the next location. Similarly, you compress these 3 bits, these 3 bits, these 2 bits, and this 1 bit. And so you have again 2 bits, 2 bits, and this is 1 bit. And now you have compressed these 3 layers into 2 layers. Okay, now you can have this layer, and again you have now, so this layer with these 2 layers, compress them into 2 layers. Again you have this layer and the 2 layers coming out of these compression tree. Again you have 3 layers, convert them into 2 layers, and again you have this 1 layer and 3 layer, convert them into 2 layers. Finally you have 2 layers of numbers, add them together. So one full adder delay will compress 3 layers into 2 layers. So vertically, if there is a dot, you only have to drop that dot because you cannot compress it. But if there are 2 bits in the layer, especially once you're doing partial product reduction, do add them using a half adder, put some here and carry to the next location, because you are going to use a full adder, which is sum in this and carry to the next layer. So that's how you go from one level to the next level. So this is how you do the compression, and using whatever I've described. So now there are many ways to do the partial product reduction. One is called carry save reduction, which I have just explained. Like first take 3 layers. So if there are, like say, 6 layers of partial products, so you have these 3 layers, convert them into 2 layers, and now take this layer, convert now these 3 layers into 2 layers. Now bring this layer and convert these 3 layers into 2 layers. Now bring this layer, and this is where you convert this into 2 layers. And once you have 2 layers, now add them together to get the final answer. This is called carry save. Dual carry save is, why not I split it into 2 parts and apply carry save here and apply carry save here. So I'm going to get 2 layers from the above and 2 layers from the bottom. So I have 4 layers. So then 4 layers I can have converted them into 3 layers and then converting them into 2 layers, and then we add. Wallace tree, what Wallace tree does is it makes pair of 3, 3, 3, 3, 3 and do the compression in parallel. Obviously, this will be the fastest. And then they are further, uh, and people have spent a lot of time because this is so core to algorithm design. All algorithms would have many, many numbers which you have to add, many numbers you need to multiply. That's what you're doing all the time. You're multiplying and adding numbers. So for example, 12 by 12 carry save adder would do this. First, these 3 layers converted into 2 layers. Okay, putting one full adder with a delay of full adder, because you put all these full adders, they will just add 3 numbers and will generate uh, 2 layers, 2 layers of numbers. Now bring this one here and again do the compression and keep doing that till the time you hit only 2 layers, and many bits you will get as free bits as they gets resolved, and then you will have a smaller adder to add the numbers. Okay, so this is a layout of the same thing, that you have 3, 3, 3, you're having full adders, and you drop the dot right here, 2 adders. This is also, so these 2 bits we call these free bits, but the next carry goes to the next layer. And now this is the next layer of numbers. So third and the fourth layer, you have full adders and half adder. You drop the half adder to the carry to the next layer, and then similarly next, and you have the next layer. So these are 3, 4, 5th, and 6th. After 6th, you have 2, 2, 2, 2, 2, 2 bits, which you use a carry propagate adder to add, and all these bits are the free bits. Okay, so dual carry save is where you split them into 3 parts and do the reduction in parallel. But interesting is the Wallace tree. Wallace tree is where you have all the 3 layers together. So you have these 3 layers, and then you have these 3 layers, then you have these 3 layers, then you have these 3 layers. So in one go, putting a full adder layer would reduce them into 2, 2, 2, 2. So 12 would get into 8, right? 1, 2, 3, 4, yeah, 8. So from 12 layers with a full adder delay, you reduce it into 8. And again, you do the same 3, 3, and 2, 3, 3, and 2. So you have 2 here, and 2 here, and 2 here. So you reduce them into 6, and 6 will be reduced into 4. Okay, and 4 will be reduced into 3, and 3 will be reduced into 2, 2 will be reduced into 1. Add. Okay, so that's how you go about doing this. More the layers, faster it will be to converge to smaller number of. So as you can see here, you have a pair of these 3 numbers and pair of these 3 numbers getting compressed at the same time with a layer of full adders and half adders, full adders and half adders. And then you are reduced by 4, then 4 reduced to 3, and then 3 reduced to 2, and the 2 is finally what you add using a. Interestingly, many a times you are adding many numbers. Okay, many numbers. So for example, it's not multiplication, but you are adding a plus b plus c plus d. You are finding summation of, let's say, many numbers, summation of ai, where I goes from 0 to 10. So it means you are adding 10 numbers. So instead of having an adder tree where you add numbers, putting 2, generate 1, then add another, and end up using 9 adders, okay, consuming 9 adders, that is very expensive. Adders are again very precious resource. We must not waste them. So the best way to do this is that you use compression, either Wallace tree, or even people have come up with, because you are using lookup tables, if it is an FPGA. So what they will do is they will add all these bits together. Let's wait for the azan to. Okay, so using the lookup tables, they may be like 5 input lookup table which you put, and it'll just add all these numbers together. And if you add 1, 2, 3, 4, 5 numbers, so what is the largest number you can get? 1, 5. Obviously, if all are 1, 1, 1, 1, so the maximum you are going to get is 5, which is 1, 0, 0. So it means always possibilities that 5 can be reduced into 3 bits. Right? So the same concept. Instead of just a full adder, you're saying there is a logic which will take 5 numbers and just add them together. Okay, using some logic, which is maybe a lookup table, is going to generate 3 bits. We put those 3 bits like this. So directly from 6 bits, you get into 3 bits. Right? 5 bits gets compressed into 3 bits. So 5 bits, you are going to have 3 bits because this is the worst that you can get. Maybe if all are 0, you only get 1 bit, which is 0. Okay, but worst is 1, 1, 1, 1. So you are going to get, if there are 6 numbers, sorry, it is 1, 1, 0. 6 is 1, 1 and 0. So 6 bits can be converted into 4 bits. So it means there is no limit if you are thinking about it like compressor is a combinational logic which can take many 1-bit numbers and can collapse them, can add them. So let's say if there are 12 or 16 or 15. So 15 is 1, 1, 1 and 1. So worst case is how many bits? 4 bits. Okay. So 15, you take 15 numbers together and considering 1 bit at location and all the bits 15 bits together, and you compress them and convert these 15 layers in one go into 5 layers. Then you take all these 5 layers, convert them into 3 layers. Then 3 layers, convert them into 2 layers. So this concept of compression is widely used in digital logic, especially once we are converting algorithms into silicon, making hardware. You don't, if you are adding 15 numbers, putting 14 full adders like carry propagate adder does not make any sense. Right? Consuming all of them, because just compress them first and then you feed it to, and where you are kind of not propagating the carry, you are just saving the carry, and just putting them at their appropriate location, and that is very effective, very effective. And you will find many research paper publications which would, interestingly, in digital logic, people would say even if you are multiplying, let's say you are saying A multiply by B, okay, like we do all the time in convolution, in correlations, and then you have, let's say, C multiplied by D. So if you think of this, these are all partial products and partial products. Okay. And then you may have many of these, especially once you are doing filtering, many of these. So it means you have hundreds and thousands of partial products which you got to compress and find out an answer. So in many algorithm, we never put a carry propagate adder. We keep our answer in sum and carry form. So 2 sum and carry, we take them. 2 sum and carry. So I will not like to compute an answer here. I would not like to compute an answer here. I would keep my answers into partial half-cooked form. And it is only once I really need an answer, I will just add them together to get an answer. Okay, otherwise all compression. So all the time you are just creating all the partial products and converting them to only 2 layers. And even if the algorithm requires it to be fed back, you feed the 2 numbers back into your next iteration of the algorithm to reduce area. This is again a very convenient way of dealing with